This is a series of videos that tell the story of how my father and I came up with the four universal motions in physics. We highly recommend that you watch these videos in order. Enjoy. Of all the human beings that have lived during the last 400 years, why did my dad come up with a solution to one of the most famous problems in physics? Today, we will tell you why. So, Dad, that's the big question. I would imagine that's one of the first things you thought of once you realized you solved this problem. You pondered on what I told you have done, but you took some time mulling that in your head. And when was the first time you really started thinking, why me?
First, I had to figure out that what you were saying was true, that there was a problem called wave-particle duality, and I went and looked at that for a while. I went on the internet and read what I could, and finally concluded after maybe several days that, okay, maybe the light solution does solve that problem. I immediately followed it with the question of myself, well, why me? I'm an engineer. I'm not a scientist. And why should I solve some great science problem? And almost out of the clear blue, because I didn't even know it was a problem. What did I do to deserve this honor? or maybe it was a curse. I'm not sure.
Well, it's interesting because even though it only took you a couple of days to figure out what you had done, you didn't come to me right away. You spent the next 2 weeks thinking, why me? Why me? Did you come to the conclusion or get any answers to that? Or you just said, the heck with it, I'm just going to go back to Dave?
Initially, no. I really think with discussions with you, it was you who came up with the answer based on knowing what some of my background was. And I wasn't tying this model to that background.
What we're going to do is we're going to take a look at the document that you had sent me before the time we had in the previous video, the aha moment where I saw that you had solved this. And even though you didn't know it yourself, you had sent me a white paper. And I went back 10 years in Gmail and I found that white paper. And it's interesting because the first white paper you sent me didn't have those round circles representing particles for light. So here it is, the famous white paper that you had sent me. And it says at the top, a particle theory of light, exclamation point, and gravity too, which is kind of interesting since now we believe it's the same particle. Actually, it's just how it moves. If you look at the bottom part of it, it says string of particles. A string of particles could give both amplitude and frequency. Figure 1 shows a string of dots with varied spacing. Each dot is a particle. It is matched with a sine wave. Particles are closer together when the sine wave is at a maximum, and they are further apart when the sine wave is at a minimum. The time of the wavelength is from one peak to the next. The inverse of the time is the frequency. So you did that, and then you said figure 1 is not yet available. And I think what probably happened was either you didn't make it, and you sent it to me, or it wasn't included at the time.
No, I remember writing the note, and my intent was to do a figure. Then inadvertently, sometime later, I sent it to you without ever going back, doing what I wanted to do. So you ended up with this document without a figure.
I went and I found another paper later on that you had sent called, I think, the EM particle. Let's see here, the EM particle. And there it is. And what's really, really interesting is that what we had thought many years later while we were writing our book was a totally different diagram, which we're going to look at. But if you look at this, it's exactly what you had described. You have a bunch of particles and they vary in their spacing. So the red dots represent the points in the sinusoidal wave that would cross a line if you're doing this just mathematically and not physically. If you buy our book, the Principia Mathematica 2, this is not what you're going to see there. We somehow had a different diagram, and because I didn't go back and look at this, I just assumed, okay, it wasn't included. And I don't know where this other diagram came from. So let's take a look at what I did later on without ever seeing this. So I didn't see the above diagram or remember it when I was creating this one. I didn't go back to the white paper. We were writing the book many years later. Lo and behold, I did sort of the same thing. And the difference here too is I put little arrows on all the particles, meaning they're all moving together like waves of bombers. But what's curious about all of this is this. Now, somehow in our book and in our journey, we thought that this was an original diagram. Now, maybe you wrote this, showed this to me, sent this to me at a different time. I have not found it yet, but the idea is they're all spaced the same and they have these particles, and there's one particle, 2, 4, 5, 4, 2, 1. You see those different numbers, and I expanded it visually, and that's in the book as well. So this is the kind of expansion to make it more visual of what's going on. So this is really curious. I don't know how we digressed from what you had already done, which is this diagram, which was the diagram you sent me originally before even the talk you gave, and I understood what was going on, to how we got to this. And then, of course, eventually, then I looked at it and says, no, it's going to be a lot messier than what that is. And so I got more what we call a more realistic, messy wave. So you don't know either where this other diagram came from, that one, right?
Well, I feel like the top one is something that I might have done.
So what you're saying is you admit that the top one probably was one of your diagrams.
That top one.
Yeah.
When I developed those numbers, I was actually looking at a sine wave and coming, let's say, close to the value, but using integer numbers.
Yeah, and there's also equal spacing, which we're going to talk about in a little bit. We'll get back to that. This is what you produced, and we got to the kind of more messy wave. In fact, here is even a kind of an animation, even though these are kind of perfect in the sense you see them kind of all in long lines. But this gives you an idea of what kind of looks at these are moving through space. So this is kind of the model we have. But if we look back in time, we're trying to figure out why Robert D. Hilster got it. And why didn't Newton or Maxwell or Einstein? Newton thought about a particle model for light, correct?
Yes, he did.
And he wrote the optics treatise for light. And in that, he had these Newton's corpuscle theory for light. Why don't you explain that a little bit?
What he has are particles, but they're different sizes. I think he was not trying to describe the frequency in terms of a literal wavelength between particles. He was trying to describe it in terms of the size of the particle being related to frequency. I think ultimately that was one suggestion he made, but I don't think he stuck with that.
So let's go forward. This is just our famous, you and I's least favorite picture of what they call an electromagnetic wave. So tell us about this diagram.
I forget who it was who did the experiment that showed that a magnetic field could produce electricity, and electricity could produce a magnetic field. In some sense, they were perpendicular. And I often use my hands to describe that. My finger is electric current. The magnetic field is a circular path around that wire, and so that circular path represented by the diameter of the circle there are perpendicular. They broke it into two separate fields, an electric field and a magnetic field. Every time I look at that drawing, I keep asking myself the question, what's causing them to oscillate up and down? They start out at zero, go up to a peak, back down to zero, down to below. You can draw that, but it's got to come from somewhere. What's the source for that wavelength that makes sense?
This is the epitome of where physics is today. There's just zero physicality. It's all mathematics. It's all diagrams. This is math. Like you said, what's causing this? What is it? What's a magnetic field? These things are magical things that people talk about, an electric field. This is a mathematical representation of somehow the forces involved, and zero, zero, zero indication of what this all could mean. It's a useless diagram. It really is,
Yeah.
because
And I get the same reaction from Maxwell's equation, because those equations are so abstract. I don't know how to relate the terminology. Yeah, the B is the magnetic field and the E is the electric field.
even before Einstein, there were people looking at ether. This is actually a sound wave in air, a model of that. But if you watch any one particle, you'll notice that it's only going back and forth. And so the proposal for the 18th and 19th century, specifically the 19th century, everybody was looking for ether. They said light has to be a wave. It has to be a wave through some medium. We're going to call it an ether. And they searched and searched and searched for it. Very famous Michelson-Morley experiment to try to find us moving through this ether. For, of course, no one ever explains why this ether would stay in one place. What does that even mean? Why would particles sit around and kind of like they do in the ocean? Well, they sit in the ocean or in the air because we have gravity pushing them down, but that's another story. But this is the ether kind of idea or model. But then Einstein came along with his photoelectric effect and said, no, light's a particle. And you have these incoming photons, and that ejects these electrons. What I just get a kick out of is, look at the diagram, whoever made this, of the photon, Dad. Look at that. It's it's this kind of oval, and it's got squiggly lines. It's a particle and it's a wave. Mainstream science and physics says light is a particle and is a wave. Again, what is that? When I saw you do your famous moving fists together, I realized light is a frequency. It's a physical thing. And the only way to get frequency is to have more than one of them coming at you. And so the idea that there is a special particle that you would call a photon is not needed. You can have suns out there. If the suns were all traveling together with a frequency like bombers, that's a lumenic wave, just as you have described. And that's why in our four motions, if you go to fourmotions.org, that's why we call these universal motions, because it doesn't matter what it is. You have to have more than one. So the idea of a photon makes no sense. So one of the answers to the question, why you, is that you spend a lot of time in telecommunications going from analog to digital, taking sound waves that were analog and converting them into digital pulses. The pulse code modulation basically breaks, it samples the sound wave in small increments, takes the amplitude of that, changes it into a digital pulse. There's different ways to do it. It's not a straightforward thing, but that's not important here. And then it sends those pulses over a wire, and on the other side, it decodes them, and then you can recreate the sound wave. Well, the second and third lines I added there, which is the Bob's light, which is the idea of that one diagram, which we haven't found, but you created at some point, which is basically, evenly spaced particles with the number of particles at that point. And then below it is what I would say is a lumenic wave, which actually took us almost 10 years to come up with even that terminology. But this is, the bottom one is my father's lumenic wave model of light, which are basically particles moving all together at the same speed, and they have amplitude by how many particles are there. They have frequency by how far apart they are. That way you can recreate any type of waveform. So we get to the question, why Bob D. Hilster? Why did he come up with a solution to the wave-particle duality? The pulse code modulation is in my dad's brain. He was working on the particle model for gravity for 10 years and decided to try, how could I make light waves with particles? Put those two together, makes a whole lot of sense why he did it. So the truth is, one in billions in the last 400 years had those two things. How many people were working so intimately with telecommunications and reproducing sound? There are people who do that, but were they also working on trying to give physicality to fields like a gravitic field and spent a lot of time on that. No, probably about anybody in the last 400 years of the billions of people, my father was the one who said light is waves of particles. And there you go. That's the answer. It's the definite answer. And so if any of you get this on Jeopardy, you know what to say, right? Does that make sense? The intense study of a gravitic field using particles, then trying to go to light and having this PCM in your head.
It's a logical connection that you can make there. What I have somewhat of a difficulty is remembering the explicit time when I made the connection and would have said to myself, wow, I just made the connection. That kind of aha moment didn't for me, didn't happen. And of course, I didn't even know about wave particle duality. And so I had done something that I had no reference to in terms of what science was trying to do or trying to understand. And so I just came up with the idea. And as I remember, I tried to get it across to you one time and didn't get anywhere. And a couple of weeks later, we were together, and I finally interrupted you and Bob Berger with this information because I wanted to get it across to you, and I hadn't been very successful until that evening.
So in conclusion, you are the only person in the last 400 years that had those two characteristics. And that's why you came up with a solution for the wave particle duality. So congratulations. We'll put an applause there.
Thank you.
All right. And you seem to agree with that, at least in part. So
so they'll probably be hanging me in effigy in the future when they find out what the real answer is. Because as you pointed out, this is like one answer. There may be a better answer, but go with what seems to work for now, and maybe at some point it fails.
What's really, really interesting, and that's why you got to keep tuned to my dad and I's conversation, because this story is a long and fascinating one, is once we got this, once my dad came up with a solution for the wave particle duality, things exploded. And we probably had the most fun in a year and a half that we've ever had scientifically. Yep. So stay tuned.